Hello students, I just wanted to remind you guys that this PowerPoint presentation is meant to supplement your reading material and not replace it. The timeline of the atom goes all the way back to 2,500 years ago, when the Greek natural philosopher Democritus speculated that particles that were indivisible were known as atoms. In fact, atoms essentially mean uncuttable or indivisible. Well, at that point, two natural philosophers were kind of the rock stars, and that was Plato and Aristotle. And they thought this idea seemed speculative and dismissed it, and in fact rejected the idea. And because of that, the idea of the atom kind of went away until a chemist in the early 1800s known as John Dalton reintroduced this idea. In fact, his theory on the atom had 5 points, 4 of which are still known to be true today. What Dalton's theory said was that these indivisible minute particles called atoms were the elements that made up all matter. The second point said that all atoms of one particular element are the same shape and mass. And we know that's not true today if you think about isotopes. The third one is that the atoms of different elements differ in shape and mass. In fact, we see this to be the case with the number of protons and electrons. The fourth one, atoms chemically combine in definite whole number ratios to form chemical compounds. And atoms are neither created or destroyed in chemical reactions. Work on the atom was later furthered by a physicist by the name of J.J. Thomson in the late 1800s. He did studies on electricity using what's called a cathode ray tube. In order to see what it is, you can either look on YouTube, or if you go to Blackboard under the video section for this week, you will see an excellent short animation showing really what J.J. Thomson did in order to prove that electrons were negatively charged. But essentially what he did is through this cathode ray tube, he moved a beam through the tube, which was deflected away from negative charges because like charges repel, and it moved towards the positive charged plate because opposites attract. And that meant that the electron was in fact negatively charged. In fact, he later used this to develop the electron's charge to mass ratio, which was later used to then find the charge and mass exactly. And then he was able to identify the electron as a fundamental particle of the atom. By using these charged oil drops in an electric field, the American Robert Millikan was able to find and measure the exact charge and mass of the electrons versus the atom. He also speculated that atoms had something neutral, or they were able to neutralize a negative charge. In other words, something had to be positively charged to neutralize the negative charge. As mentioned, using J.J. Thomson's work, Millikan was able to actually find out the mass of the electron. Early ideas of the atom were very interesting. Dalton had looked at atoms as indivisible in the early 1800s. And then Thomson and Millikan did these experiments where they were able to calculate the electron mass, which was very small, so there was no actual measurable volume. And then they wanted to know what is the nature of the atom's positive charge. So Thomson had what later became known as the plum pudding model. I don't think that was his actual name for it, but what he thought is that atoms were this positively charged blob, and that the the electrons were scattered about that blob. And because he was British, they thought it looked like the idea of plum pudding with raisins scattered about in the plum pudding. Now we know there's more of an orbital model, but at the time, this is what he speculated. One of Thomson's students, Ernest Rutherford, who actually won the Nobel Prize for this work, used radiation in the way of scattered alpha particles that he passed through gold foil. Using the plum pudding model, he thought that they would actually all pass completely through the foil to the other side. In order to really see what this looks like, I do recommend that you watch the short animated video on Blackboard. But instead, what he saw is that some of the particles actually deflected and hit the indicator screen or the detecting screen behind the gold foil instead of passing through it. It was very few. In fact, they calculated exactly how many times that happened. But what that did is it told them that the plum pudding model was not true, but rather atoms have a nucleus that the electrons actually rotate about. Rutherford's work not only figured out that there was a positively charged nucleus that was surrounded by electrons, but he also found out that there was these protons, in other words, these discrete units of positive charge. Later, a scientist by the name of James Chadwick in 1932 found that there were additional particles known as neutrons. These neutrons live in the nucleus as well, and they are neutral particles. While they do not change the charge, they do change the mass of the atom. This is where it gets really fun, but also really complicated. So if this isn't helping and reading isn't helping, there are several excellent videos if you just do a search online for atomic number, mass number, and electrons that really break down how this process works. But essentially, in the nuclear atom, we have this idea of an atomic number, which is the number of protons in the nucleus of an atom. This number you can see at the bottom left of the element. And then at the top, you have the mass number. So the top left is the mass number, and they are actually related. So what I'm going to walk you through is what we're looking at with this hydrogen 1, hydrogen 2, and hydrogen 3. These are essentially isotopes. They are the same element. They have the same number of protons, which identifies this as hydrogen, but they differ in their number of neutrons. Remember, neutrons were the neutral particles in the nucleus. They do not change the charge, but they do change the mass. So if you look at the very first one, it says, if you're looking on your phone, it might be hard to see, but next to hydrogen, on all three of these, the bottom left, the atomic number is 1. That means that there is 1 proton for hydrogen. It also means that there is 1 electron to cancel out the proton. Okay, next, if you look up, is the mass number, and notice across the three that changes. The mass number on the first one is 1, just like the atomic number, because there are no neutrons to change the mass, so it will be the same. This is the most common isotope. In fact, there is over 99% of the atom, of the hydrogen atoms are actually this hydrogen 1. So we just call it hydrogen. Sorry. Next, you'll see hydrogen 2. What that is notice you still have the 1 at the bottom because the atomic number for hydrogen is 1. But now the atomic mass is 2 because the neutron adds that extra bit of mass to hydrogen. Now the third one has 2 neutrons. In fact, this is a radioactive isotope. And it has 3 neutrons, and it's not even counted in the number of the atomic mass, which we'll get into later, as far as knowing what percentage is hydrogen 1 versus hydrogen 2. Hydrogen 3 does not count on that atomic mass because of the fact that it is radioactive. Remember that isotopes like these three, they have the same number of protons. What makes it hydrogen is the one proton. And they differ in the number of neutrons. It doesn't change the atomic number or the charge, but it does change the mass. Once again, the mass number is going to be made up of a sum of the number of protons and the number of neutrons. And we have what's called an atomic mass unit. The problem that we had was that the mass of one atom of an element is too small to measure. And the solution to that was to compare the mass of one atom to an atom from another element. In fact, the element that they used is carbon, specifically the carbon-12 isotope. And because of that, it's relative. It is not a true mass, but a relative mass that we call the atomic mass unit. Now, the atomic weight for an element is calculating the average mass for all the isotopes of an element based upon each isotope's relative abundance in nature. In other words, hydrogen 1 makes up more than 99% of the hydrogen atoms, and hydrogen 2 makes up less than 1%. So the atomic weight will be closer to 1, or the weight of hydrogen 1. Whenever we think of an atom, we really picture this orbital model that looks a lot like a solar system, with the nucleus being the sun and the electrons orbiting around the nucleus. That is only partially true. The reason why we cannot have that model exactly like the solar system is that the electrons then would be traveling on a curved path. And as you recall from our chapter on motion, that a curved path means that the velocity is always changing. Not the speed, but the velocity, because the direction is changing. Well, when you have a change in velocity, you have what's called acceleration. And if you have acceleration, that means the charges radiate and the electrons can lose energy and spin into the nucleus. If this happened, then we wouldn't have an atom. So obviously the solar system model does need to be updated, and in order to overcome that change in acceleration, what we have is this more of an electron cloud is really what it looks like, where they kind of dance around the nucleus rather than orbit around it. Let's talk about the periodic table. Looking at the periodic table, if you look at the groups horizontally, you'll see rows. Each of these rows are called a period. So you can see hydrogen is in period 1, lithium 2, sodium, which is Na3, and so on and so forth. If you look vertically, each column is called a family or a group. So the first column would be group 1. And we actually call these groups A and B, A being the main groups or the representative elements, and B being the transition elements or transition metals, which we'll talk more about at a different time. The family indicates the number of electrons in the outer shell. In other words, family 1 has 1 electron in its outer shell, 2 has 2 electrons, 3 go on all the way over to B boron, that has 3, and then all the way over to Ne neon, that has 8. The one exception to this is helium, which should have 8 because it's in a group 8. However, it only has 2. Looking at the periodic table further, as I had mentioned, the horizontal rows are periods and the vertical columns are the families or groups. Now the family identifies the number of electrons in the outer orbitals, which also is going to be the reactive electrons. Because of this, any elements in the same family or group are going to have very similar properties. So if you look at the very first column, you have group 1A. These are the alkali metals, all except hydrogen, which does not fit into this category except for the fact that it has one electron in its outer shell. The alkali metals, as mentioned, all have one electron in the outer shell. They have a low density. They're soft metals, which they are highly violently reactive. In fact, there's a video for this in Blackboard that's excellent. They're so reactive that they do not naturally occur in nature as pure elements. The second group, group 2A, these are the alkaline earth metals. They have 2 electrons in their outer shell. They're soft and reactive, but not as reactive as 1A, the alkali metals, and it's because their outer shell is full with 2 electrons. Now if you skip down over to 7A, which starts with F at the top, and it is known as the halogens, or halogens. And if you look, there's 7 electrons in its outer shell, and therefore they need 1 to complete that outer shell. This makes them very reactive nonmetals. In fact, they are usually disinfectants such as bleach, but they can combine with metals to form what we know as halogen light bulbs. They can also react with metals to form salts, and in fact halogen actually means salt former. And then that last group, 8A, it's also known as the noble gases. We call them noble because they are so high and mighty they don't want to react with anything else. And the reason for this non-reactive property, which we refer to as inert, they are inert gases because their outer shell is already full. And they're also known as the rare or inert gases. In order to help visualize what I mean by outer shells, I use carbon as an example. First, look in the very center, that's the nucleus. It's composed of neutrons and protons. In fact, because it's carbon and the number of protons determines the element, we have 6 protons because carbon's a 6-proton element. That means we also have 6 electrons. The inner shell gets full with just 2, leaving the other 4 in the outer shell. Remember that the chemical behavior is mostly concerned with the outer shell electrons. We call these the highest energy level electrons. This picture to the right shows the electron dot notation. This is only looking at the electrons in the outermost shell or outer orbitals, the highly reactive electrons. Let's talk about how they can gain and lose electrons. So the noble gases, they have filled shells. In other words, they're inert, besides helium, of course, which only has 2. They're inert, their shells are full, they're very stable, they have no need to lose or gain electrons. However, in the first 3 groups, 1, 2, or 3, their outer electrons, they tend to be a little more unstable, and they can get lost easily and gained up by another atom that will become an ion. When these first 3 groups lose their electrons, they get a positive charge, and we'll talk more about that in a second, talking about lithium. These are the metals. Now, the second thing that we're going to talk about is the groups 5, 6, and 7. They have outer electrons of either 5, 6, or 7 outer electrons in their outer shells or outer orbitals. And they tend to gain the electrons that are lost by these group 1, 2, and 3 metals. So they gain electrons and then they form negative ions. So let me just summarize this for a second. If you have an atom, it has the same number of electrons and protons. However, if it becomes an ion, no longer referred to as an atom, but an ion, then it's going to get this positive or negative charge. And we'll use lithium as an example. It's a group 1, it's in the family of group 1A, and that means that it has 1 electron in its outer shell. It has 2 on the inner shell and 1 on the outer shell. If we turn it into an ion, how would we do that? Well, an atom of lithium has 3 protons. In other words, 3 plus charges, and 3 electrons, 3 negative charges. The 3 electrons are situated so that the first 2 are in the innermost shell. They are not very reactive, whereas you have 1 in the outer shell. That one can spin off by itself, and then you would have a difference of only 2 electrons or 2 minuses and still have the 3 protons or 3 pluses. In other words, it will have a +1 net charge. So therefore the lithium ion has a +1 charge. As you can see, the periodic table of the elements can really be divided into 4 groups. The first one being metals, which are 80% of the periodic table. Then to the right, we have the noble gases. Then the greenish color, that would be our nonmetals. And then right in between the metals and the nonmetals, we have what's called semiconductors or metalloids. And they're called this because they can actually take on properties of either in certain circumstances. Well, the metals, as we already talked about, they tend to lose electrons, and because of this, they result in positive ions. However, the nonmetals are elements that gain electrons, and thus they form negative ions. Why are all of these things important? Well, in the next chapter, we will be looking at chemical reactions, and ions are very important, as well as the different properties. So why do we learn this? Well, you'll see.